Log on, tune in, find out. Another good idea from Cambridge.
I'm particularly impressed that he's stuck to mission. He's the person who's probably got the most appropriate title for this workshop, so I hope the talk matches the appropriate title.
Probably not sure.
Yeah, so I just came up with a title that has nothing to do with my talk, but I figured I had to trick people into coming to at 9 o'clock a.m. So I'll be talking about some recent projects that vaguely can draw an umbrella over as this practice-driven cryptographic theory theme, and it's joint work with a bunch of fantastic people, so I should give them all the credit for all the good ideas, and all the bad ideas are mine alone. Okay, so the starting point for this is cryptographic standards. We got lots of them, and one of the things that I think we've seen in this workshop is that standards really are one place where the academic community interfaces with industry. But unfortunately, standards, let alone the implementations that realize the protocols within our standards, have a relatively poor track record in terms of security. Right? So here's a few common and widely ubiquitously used cryptographic protocol standards: TLS, SSH, IPsec, and just a sampling of citations from the academic literature on various ways to break these standards. So what we want to do, of course, is gain better confidence in the security of our standards, right? And that's what the thrust of this work is all about. So fortunately, we seem to have some very powerful formal tools for applying in this domain. In particular, you might have heard of this idea of provable security. And basically the workflow, or the idealized workflow of provable security, goes as follows, right? We start out by precisely defining mathematically what it means to break a scheme, right? So we identify an attack model and attacker goals. And then we set about designing a cryptographic scheme that will achieve these goals. And often we do this with having a proof in mind, right? So we kind of tweak our scheme so that we are able to do some type of proof. And indeed, the next step is establishing a proof that no one is likely to ever break our scheme. So what does this mean more particularly? Well, we set out some formal definitions, semantic security, and then we provide a proof. So working within some abstract model of reality, we show that if you give me an attacker in this model that can break the scheme, then I'm going to show how to use that attacker to break some underlying primitive of our scheme. And so we'll try to make very judicious choice of our underlying primitives, something like RSA or AES. And this gives us a potentially very powerful guarantee, right? So we show that, for example, an attacker that can learn a bit of information about some message, well, that implies that we can show you how to invert RSA. So of course, we expect that no one can invert RSA, right? And so this gives us this contrapositive that attackers aren't going to learn anything about encrypted messages. So a very elegant framework dating back to the 80s, Goldwasser and Macaulay. Fantastically powerful stuff. So it would seem that our job is kind of done, right? The story is over. Well, we can sit down with the practitioners. Theoreticians and practitioners can sit down, meditate for a while, and work out better standards with improved formal evidence of security. So this would be nice, and I could go home early from this workshop. But of course, that's not what happens in practice. And from an outsider's view, I haven't sat on standardization committees, but it sounds to me like it's more like this picture over here than the blissful green pastures. Standards are developed in a very complex manner. Lots of players involved. There's lots of non-technical considerations in terms of what gets in the standard. And then from the theory perspective, often standards are developed without help from theoreticians, or more interesting and particularly relevant for the standards that Shu showed before, they were developed in a setting where we didn't actually have the right type of theory for helping the standard. So, this leaves us with lots of existing standards out there that aren't developed in this way, and new ones are not necessarily going to be developed in this kind of idealized setting. So what do? Well, traditionally, I think we have this viewpoint that theory academics are going to help educate standard designs. And so today in this talk, and this is kind of the ideal way of doing things, but in this talk we're going to do something different. We're going to instead try to build cryptographic theory around existing standards in a post facto process. And so really switch this kind of information flow backwards. So we're going to go look at existing standards and develop theory around them. So more precisely, have a little bit of a recipe for meta-level analysis. Pick some standard that's popular and widely used. Go read it, which that's already a lot of fun. I can hear a few people who've probably done this laughing. And try to extract from this the implied security goals, match them to existing formal definitions from the academic literature, or, as we'll see more interestingly, have to provide new formalizations that didn't exist in the academic literature. And then try to analyze the schemes as specified, as best as we can tell from the standards, within this formal framework using provable security. And the output from this is either attacks, showing that the scheme didn't meet the goals that we now formalized, or proofs to clarify security. I guess I should say that there is a third thing which we have no idea whether there's attacks or proofs, but as we'll see in these projects, we can kind of do, well, actually we'll have an example of that, I guess, at the end. So, but this is the goal, to find attacks or proofs. And this gives us increased confidence if we get proofs or yields a vulnerability finding tool, right? That we can use provable security now as a way to suss out subtle problems in the standards. Okay, so this is kind of the high-level view. Have 3 projects that I'd like to talk about. The first, we already actually saw quite a bit of talk about from Tom Shrimpton on Monday, and he covered this quite extensively. This is a joint work with him and Kenny Patterson. And there, so I won't talk about this in this talk. I'll just mention again what we did. We looked at the TLS 1.2 record layer protocol and extracted out some new definitions in terms of length hiding authenticated encryption, which seems to be the security goal underlying the record layer. And then we tried to prove something about it. And in doing what we realized is that we couldn't prove the security result that we wanted to. And what this led to was the realization that there was an attack, right? That there was a vulnerability for certain parameters. And so we figured out the attack, and then we figured out, well, if we carve off the parameters under which the attack works, then we can provide a proof for the rest. So I consider this a success of this viewpoint of looking at standards first and building some theory around them. So I won't talk about that further. What I will talk about is these other 2 projects. One is on password-based cryptography, in particular PKCS number 5. And here, this is a project that when I started I thought was going to be immensely boring. Nothing could be more boring than password-based cryptography to a theoretician. And I was pleasantly surprised that, in fact, I was expecting just to prove what everyone intuitively assumed was correct about these, what's true about these schemes. But and we did, in fact, do that. But what happened is we actually needed to define a whole new definitional framework in order to tackle this problem. And so I'll talk about that. And then I'll talk about using HMAC as a general purpose cryptographic hash function. And this comes up in a few different other standards, in TLS and in PKCS number 5 as well, and a few other places. We saw a bit of this in Ugo's nice talk about HKDF yesterday. And we'll, again, use this approach to uncover potential vulnerabilities, basically a caution sign that we need to think very carefully about using HMAC in some settings. And in particular, we'll show that we can rule out a particular proof approach that most theoreticians would have assumed is the natural approach here. Okay, so I'm going to talk about these 2 projects in more detail. So great, let's look at password-based crypto. The basic setting is we have a standard encryption scheme. One could think of CBC. You shouldn't use CBC by itself. You should use an authenticating encryption scheme, as we discussed extensively yesterday. But just for the purposes of the talk, think of CBC at the moment. And CBC mode, it expects a cryptographic key K that's a uniformly chosen bit string of, if you're using AES, 128 bits. But all I have is my password, 1, 2, 3, 4, 5, right? Very strong. And I'd like to encrypt something under my secret password. It expects a uniform bit string. I have my password 1, 2, 3, 4, 5. What do? Well, the answer's been around for many decades. The solution is to use a password-based key derivation function, PBKDF. And this is exactly what PKCS number 5 specifies. So the simplest construction in PKCS number 5 is this iterated hashing construction. So you take your password, you generate a fresh, uniformly sampled salt, and then hash the password concatenated with the salt. A few other probably data items that go in there as well, but that's the main ones. You hash that, you get the output, you hash that, you get the output, hash that, et cetera, et cetera. You do that C times, where C is called the iteration count. And you end up with a bit string that we'll call K that one can then truncate to use appropriately with the standard conventional encryption scheme. Now, okay, so the full encryption algorithm for password-based encryption then is you take your password message. For each new message, you choose a fresh random salt. You derive your key K, as I showed. Then you encrypt, and you output both the salt and the ciphertext. Right? You need the salt in order to decrypt on the other end.
From a theoretical point of view, what's the point of the C times?
We'll get to that. Yeah. As a hint, it's to provide key stretch, right? Amplification. Okay, so perhaps surprisingly, perhaps not surprisingly, because of the inferred boredom factor, this security of this construction has never been analyzed in the academic literature in a formal provable security way, which is somewhat unfortunate, I guess, because everyone uses password-based crypto all over the place. Okay, so we tried to apply we did apply this practice-driven kind of theory approach. So the first thing we had to do is find suitable definitions that capture the type of security goals underlying the PKCS number 5 standard. And in particular, what we realized is that we need a new framework for discussing what we call multi-instance attacks. And in particular, this models and allows us to measure the role of salts in providing some independence between different instances and in increasing the difficulty of breaking, say, more ciphertext from different users. And what we found very interesting technically was that this new multi-instance attack setting is quite challenging to work in. A lot of our existing proof techniques kind of either go out the window or more difficult to apply. So then we return to our goal of PKCS number 5 security, and we indeed show we overcome some of these hurdles with simulation-based techniques, and which we think are pretty broadly applicable, and capture the security of PBKDFs, and use these to prove the things we actually intuitively thought were the case about PKCS number 5. So the first question you're probably asking yourself is, why do we need any new theory? This seems like a very well understood goal of password-based encryption. We can just use some of our existing tools that model encryption. So in particular, we could turn to our standard definitions of security. For example, indistinguishability under chosen plain text attack, or equivalently semantic security. And what does this ask for briefly? We have an adversary A that's going to play a game with a challenger, which is in the gray box. The adversary is going to query two messages, M0, M1. The box is going to sample a password from some probably small space of passwords, sample a bit B uniformly, and then give back to the adversary an encryption of one of the two messages according to the coin flip B. The adversary's goal is to figure out B, so he outputs a bit B prime, and we measure the adversary's success by the probability that he actually got the bit minus the trivial probability of success, which is 1/2, right? He could just output a random bit. And that's, whoops, that's fantastic. Oh, cool. Too many buttons on this thing. Good, so that's our classic definition. So indeed, a corollary of our later results is the following type of theorem statement, that if we model the hash function underlying the PBKDF as ideal, as a random oracle, we can show this type of IND-CPA security holds up to about Q over C times N, where N is the size of the space of that the password was drawn from. Okay? And so that seems great. We have an upper bound on security. We can also show an easy, well-known brute force attack. Gives us a lower bound that's basically tight. You can brute force recover a password in about CN hash computations. And here we already see the role of C, as Nigel was asking about. C helps us because we can increase C to increase security, right? Because as C goes up, the adversary has to do more work, more hash computations in order to break the encryption scheme.
So this is assuming a uniform distribution of the D?
Yes, yeah. Yeah. We have a more general thing in the paper, but for the talk, yeah.
Password is chosen for each call to the call.
Yeah, I'm just showing, again, for simplicity, the single query version. But normally you would have multiple queries for the same password. Indeed, that's what we do in the paper. Okay, so there's two unsatisfying things about this. One is kind of fundamental. In practice, n is too small to provide a very strong guarantee, right? If we have 6-digit lowercase alphanumeric passwords, gives us something like n approximately 2 to the 31. We set C equal to 10,000, which is like the suggestion in WPA and other places. Then you get, if I did my arithmetic correctly, which is always a good question, something on the order of 2 to the 44 for Q before security is gone. That's not very big by cryptographic standards, and of course, my password 12345 is not going to provide as much security. So this is fundamental. I mean, we can break a single instance in this time, but it's a little bit unsatisfying. We'd like to be able to say more. The second thing, which is interesting here, is that salts never arose in our analysis. So from the viewpoint of IND CPA, we might as well not have salted, at least at all, right? So theoreticians have given out some new wisdom here. We don't need salts. We can save all that space, which of course is a ludicrous idea. But it raises this interesting question: why are we salting at all if our theory doesn't have anything to say about it? Okay, so what this is where we started. I was very, like, well, I don't know, salts, are pretty important. So what's going on? Maybe we can say something more here. And what we realized is that you need to move to a different setting to understand the role of salts. So in particular, we can look at a multi-instance attack setting. So now the adversary, let's just consider a setting where the adversary gets the encryptions of little m unknown messages, independent unknown messages, under very different passwords, independent passwords, let's assume, chosen from the set D. Well, we well know that the best known brute force attacks work as follows. If you didn't have salts, right, say we followed my odious suggestion from the previous slide and got rid of salts, well, we can build rainbow tables and do a nice attack that works in time about C times n plus m times n to recover all the messages, recover all the passwords, and then recover all the messages. Okay, but with salts, this moves to m times C times n, right, which is much worse as m grows. So what this shows is that actually salting provides a nice kind of line of defense, right? Okay, you might be able to break one instance, but as you go to more instances, the best known attack, well, it's going to grow in complexity with the number of instances you target. So you get this second line of defense. Okay, so this is the best known attacks. Having this provable security viewpoint, we'd like to say something formal about this to show that this is the best possible attacks, rule out any other attacks that might come up. And indeed, we think this matches our intuition that we should be able to show something like this, that any attack to break M encryptions requires MCN time. Okay, but now we need a definition, right? Because we saw IND CPA didn't do it for us. So let's try to derive a definition that will be able to measure this type of multi-instance setting. And the first place we will start is the most natural, the multi-user setting. It's like only edit distance of 1 away from what we're talking about based on words. So it's a natural place to start. This is due to Bellari, Boldriva, and Macaulay back in 2000, was proposed in the setting of public key encryption. And there they basically say, okay, well, if we have, let's look at the 2-user setting. We'll replicate our game so that an adversary A now gets to interact with 2 different challenging oracles. And what they did in particular was they said, okay, we'll have a challenge bit that's common to these two boxes, but otherwise the boxes are independent, okay? And this worked for the setting they're investigating, but unfortunately doesn't work for us because it's easy to see that as soon as you recover either PW1 or PW2, you learn the bit B prime, the bit B. Okay, so that doesn't help us. So, the next step, of course, is to take 2 different bits, right? 2 different challenge bits across the 2 games, and have none of these boxes are basically completely independent except for the adversary's interaction with them. And so then the question becomes, well, now what are we measuring? It's no longer there's just one bit to learn, but there's two. So the natural suggestion is to, well, ask the adversary to output both bits, to learn both bits, right? Underline both of these instances. So we can have him output 2 guesses, and he wins if he gets both bits correctly, and then we'll subtract off the trivial success probability of 1/4, right? Because you can just output 2 random bits. Okay, this is what we call the AND measure of multi-instance security. But it's unfortunately very awkward to work with. It doesn't really capture what we're trying to get at. And to see that, you can think of, well, an adversary that breaks the first password, password 1, and just outputs a random bit for the other instance. We would expect this to give you advantage 0, basically, because you haven't really won the game. You haven't won against both instances. But instead, what you get is advantage 1/4, right? Because you've learned one of the bits and you guess the other one. You get that with correct probability 1/2. You're good to go. That's a little bit unsatisfying. It's very difficult to work with as well. So instead, we propose a new measure, which we call the XOR measure. So the adversary goes back to outputting just a single bit, B prime, it's his guess. And he wins if he learns the XOR of the 2 challenge bits, B1 and B2. Yes?
If you're using a random oracle to derive the key,
Yeah?
isn't indistinguishability equivalent to recovering the full key?
That would be true, but we're not interested in figuring out what's true for this particular scheme. I'm trying to figure out what is the appropriate definition of security at all for multi-instance attacks for encryption. But your intuition is correct, yes? Yeah.
Often in the real world, an attacker might be quite content just to recover 1 out of n passwords.
That's true, yeah.
And then your original definition is probably fine. So
No, it's not, because actually the attacker, if you have m instances to try against, and you really just care about getting 1 instance, you actually have an advantage, right? Because you can play against all these instances at the same time, potentially learn which one to break. So I'm not going to talk about them here, but we deal with that problem. We allow adaptive corruptions as well, but I won't go into the details, but exactly for that reason. And also because we may not be interested in just learning all M encryption, but maybe half of them is also important, of course. And we just want to show that with the fraction of uncorrupted instances, that's the scaling you get in terms of security. Okay, so this is the XOR measure, and it gives us what we expect for this particular adversary A that I just described that breaks the first one and just guesses the other. He has no information, it just gives you advantage 0. And it's the well-known sensitivity of XOR that gives us this. Okay, so that took us a little bit of work, actually. We puzzled over this for quite a while, like what the right type of measures are. So we were pretty happy when we came up with this idea. Okay, so generalizing out from encryption, you can kind of give a general framework for getting multi-instance security notions from single-instance security notions, traditional ones like IND-CPA or unforgeability or key recovery, etc. And as I mentioned a second ago, we do include an ability to do adaptive corruptions, which covers some of these corner cases not covered by just asking that he corrupts all of the instances. And I should say we only showed the 2, right? But you can, of course, make it go to M very easily. What ends up interesting in this setting is that things get harder. So for those of you who are more on the theory bent, this seems like a very technically challenging place to play in. For example, hybrid arguments, which are a classic tool in the single instance setting, we can use those here, but they become harder to apply in a meaningful way. In particular, the factor 2 loss you typically have ends up incurring like a factor 2 to the m loss in this setting. And this makes for some interesting issues. For example, that real reverse random ciphertext indistinguishability can be quantitatively weaker than left or right indistinguishability, which is like the opposite is true for the most part in the single instance setting. So strange things kind of arise and challenges arise, which I find very interesting. Okay, wandered off the theory land. Let's get back to passwords, right? We wanted to say something about this. To overcome some of these challenges, we introduced indifferentially styled simulation-based PBKDF security notion. And this overcomes some of these difficulties that we encountered. And I won't tell you anything more about it. I'll just give you the statement we finally get, which is that in the model where H is still ideal, we can show the security of this scheme does hold up to what we expect, Q over M times C times N, plus a bunch of other terms that should be smaller for good instantiations. And this is exactly what we thought intuitively, right? So there's no surprise in what we can prove. The surprise was in how hard it was to prove it. And we think that this multi-instance attack thing is going to have other applications. I mean, you can start looking at for anything. Passwords are the most well-motivated because we know each single instance has very little security, but you can think about it for any other type of cryptographic primitive as well. Okay, so let me move on. Talk about HMAC now being used as a general purpose hash function. And yeah, let's just get right into it. So HMAC, as you probably know, is a keyed hash function. It was proposed by Bellari, Canadian Crofcheck back in 1996 in the setting of message authentication. So it takes a key K and a message M and works as follows, given an underlying hash function H. And I'll just show it for the special case where the size of the key is equal to the size of the underlying, the block size of the underlying H. It looks like this. You take the key K, you XOR it with a constant iPad. You concatenate the message to it, and then you hash it. You take that output and prepend to it the key K XORed with another constant, OPAD, and then you hash that. And that's HMAC of K, comma M. Okay, so it was originally proposed, as I said, in a setting of message authentication where you use K as a shared secret key that's uniformly distributed. And we have very nice proofs of security in this setting from the original paper and some sharper ones, some sharper analysis later on by me here. And so that's all well and good. But the thing is that HMAC now is being used in a variety of settings that are different than this originally proposed setting. So for example, in places where the key K ends up being a public salt, we saw an example of that with the HKDF construction from yesterday. Also, already in TLS 1.2, HMAC is being used with a key K that's not a uniform secret value. It's something else. And in fact, also in PKCS number 5, which I was just looking at, we end up using K as a password. And this is some academic suggestions that this is actually where I first started thinking about this problem. We also proposed using HMAC in a setting where K is not a uniform secret, and first came to our attention that this new setting arose. So the question is, of course, given our viewpoint here, can we support these other uses with proofs of security? Let me skip this example in the interest of time. This is the academic suggestion. We'll just go back to PKCS number 5. And so what I showed you before was one of the two PBKDFs that are given in that standard. This is the other. Well, it's a slightly simplified version of the other, but this is the core of it. And what it does is it takes the password and uses that as the key with HMAC, and takes the salt and puts that as the message of HMAC, and then applies HMAC. You take that output and you're going to use that as a message with HMAC again, with the password again keying, and you do this C times to get this iteration count C as with the single hash case. So the first thing to note, my password of 12345 is not a uniform secret key. So something's a little bit different about how we're using HMAC here than in traditional message authentication settings. But we do have this sense that we should be able to prove something about this if HMAC behaves ideally, like a random oracle. Where here we mean a random oracle in both K and M. So as you input different pairs, you get random outputs. Okay, so we apply our approach. And in particular, in the first case, we seem to have a job already done for us. That in the formal literature, there's a notion called indifferentiability from a random oracle due to Maurer, Renner, and Holenstein, which seems like the appropriate goal to show about HMAC in this more general setting. But unfortunately, we show that it doesn't seem that we can prove anything meaningful about HMAC security in this sense of indifferentiability from a random oracle. So in particular, we rule out proofs of indifferentiability for HMAC, even when the underlying hash function is itself ideal. And this was quite surprising to us. We again thought that this was going to be a kind of straightforward exercise to prove something interesting about HMAC here. What this led us to figure out what the deal was is we found that there's what I'll call like a warning sign about using HMAC in some particular settings. We have no reason to believe that any of the settings where HMAC has been suggested for use in this way have actually any vulnerabilities. But that said, we can't prove anything about their applications there. So let me give you a brief overview why indifferentiability seems like the right goal. So we can look at, again, password-based encryption. And now we're using HMAC as our PBKDF in the way I showed before. So what we can say in this setting is, well, we can actually apply our theorem from the prior section, right? If we model HMAC, all of HMAC as a random oracle, then we can just apply our previous proof basically as is and get the type of guarantees that we were targeting for PKCS number 5. That's great, but what this asks is that HMAC actually, is a random oracle. So a random oracle here being, a procedure that takes an input and consistently maps each input to some uniformly selected output point. So, as we saw before, HMAC looks like something like this, at least in one particular size of K. And so the questions are, is this a good assumption to be making that HMAC is a random oracle, even though it has this type of structure? Okay, well, indifferentiability gives us a seemingly nice way out, and a nice way out in many settings, which just won't help us here too much, which is the following. Basically, there's a composition theorem from Maurer, Renner, and Holenstein that says, look, if you have a proof like we had before, where you assume HMAC is a random oracle, and you additionally show that HMAC is indifferentiable from a random oracle, particularly in a setting where, say, the underlying hash function H is ideal, then what you get for free, basically, is that the encryption scheme using this PBKDF is secure using HMAC, okay? So you get this goal, this conclusion that we want somewhat for free. All we have to do is show indifferentiability, okay? So this is, we didn't point out this would be a good place to look, and Croft-Check and other people. It's like the natural approach in this setting now that we have indifferentiability from several years ago. And indeed, showing indifferentiability of HMAC would be really useful because all of these settings that I mentioned before, we'd have at least some proofs of security to support their use. Okay, so the problem comes up that we show that you can't prove HMAC's indifferentiability with good concrete security, at least suitable for some of these applications. So the implications, before I kind of give you a sense of why, is, this doesn't give us any vulnerabilities. All it does is rule out one way of proving security in this setting. So what it does say is we'll need new strategies to analyze HMAC security when this is, the results that we rule out apply. And what we do feel is that there is some concern that in some settings there might be a little bit of an issue, but it seems, basically we need more analysis, so we need to figure out more stuff. So instead of talking about HMAC, which is a little bit more complicated, let's talk about a related function, which is simpler, to give you a sense of what the issue is. And this is particularly a suggestion due to Ferguson and Schneier, not in applied cryptography, but in cryptography engineering, I think, 2003, or practical cryptography, 2003. Anyway, the suggestion was to the second iterate of a hash function h. So you take a message m and you apply h to it, and then you apply h to that, and this is our new hash function that we'll call h squared. And this was suggested to stop length extension attacks, in fact, which is also what HMAC was suggested to stop. So a slightly different approach for a similar problem. So, okay, we can ask the same question basically about this. Is this second iterate of a hash function h indifferentiable from a random oracle? Does it behave like a random oracle? Okay, we've gotten rid of keys and everything's now. It's just kind of a cleaner question. And indeed, the intuition would be that if h, we'll assume that h is itself ideal, right? It's mapping inputs to random outputs. Then surely h squared should be also good in the same sense, right? So unfortunately, that's not the case. There are structural properties in this hash function that aren't, this hash function h squared, that aren't present in a random oracle. And just algebraically, we can see that there's this seemingly innocuous property, which is that if you have the fact that h squared of h of m is just equal to h of h squared of m. This is true of any second iterative of a function, right? So you can basically shift it over one, compute inputs to outputs. There's this relationship. If we go to a setting where we're iterating h squared c times, this also holds true, right? And I'll show visually this in a second. It turns out this kind of, we call it a chain shift property, but it's a general property second iterates, causes problems when you try to prove security of, in the sense of indifferentiability. So let's consider length c chains of h squared starting at some point m. So we basically apply h squared now, c times. All right? And finally get some output. This is actually exactly like the way PBKDF number 1 works, or would apply h squared if h squared was the underlying hash function. So if we expand out what h squared is just 2 applications of h itself, right? So you get 2c applications of h, and we label all these internal variables. Okay, so the thing is, if you give me m and k, so the input and the output of this chain, then it's really easy for me to compute a new chain that's of length c, m prime, k prime, with just 2 h calls, right? So in particular, I'll just set m prime to be h of m, so this value v1 prime, and then I'll also hash the output of the original chain k to get a value k prime, which is one more application. And then what we've done is we've just shifted a chain over by 1, right? And now I have a new chain, m prime, k prime. Okay, nothing surprising, but the issue is that, in fact, the 2 chains that we have here are completely disjoint with overwhelming probability, right? Because the second chain is kind of the intermediate values plus 1 extra of the first chain, right? And they aren't going to overlap with high probability when h is ideal. Okay? So that seems interesting. So, okay, I mean, whatever, we can do this. That's fine, some property of second iterates, or of any iterates. And let's go look at what happens in the random oracle setting where we replace h squared, the all of h squared, with now a random oracle. And the question is it similarly easy to compute given a C chain, mk, a new disjoint C chain, m prime, k prime? And the answer is no, it's not. And it really requires C calls to the random oracle C application of the hash function with high probability. Why? Because of this disjointness condition, right? So of course you can do the same thing. You kind of do 2 queries, but then you get a chain that overlaps with the first chain. And so it's the disjointness that doesn't get satisfied there. Okay, so even if you didn't understand all of that, I mean, the takeaway is that we have this fact that there's this, you can compute disjoint C chains cheaply with h squared, but you can't do it cheaply with a real random oracle. And in this way, we have a way in which this construction h squared differs or fails to behave like a random oracle. Very strange esoteric property, but still a smoking gun in the sense of there's something going on here with the structure of h squared. Okay, so this intuition underlying the C chains example helped us build an attack on the indifferentiability of HMAC. This is an attack on the applications of HMAC, but an attack on the indifferentiability of HMAC, and also on h squared. And I should say, of course, that HMAC has a similar property to this chain shift property that's exhibited with h squared. And so in particular, for those of you who've worked with indifferentiability before, we show a theorem that roughly says that we can give a distinguisher for any simulator S such that the advantage of this distinguisher is lower bounded by this term, 1 minus q of sub s squared over 2 to the n minus q sub s over q squared. Don't worry about that if it makes no sense to you. The point is, what this shows is the simulator has to do a lot of work to try and simulate properly. And this is problematic when we want to use indifferentiability as composition guarantee that I talked about before to provide, to conclude security in the settings of interest. So that's basically what I said a second ago. This seems to rule out, in many of these cases, providing the types of security results that we would want in these newer applications of HMAC. But again, emphasize that this doesn't yet imply any attacks at all. We've just ruled out a proof approach, okay? And basically, we're going to have to go back to the drawing board to understand why, what else we can do. And I should also say there's actually there's some easy fixes for this. right? It's something I didn't mention before. We can just do a little bit of domain separation for HMAC, or fix some bits, or just restrict the key length to be not exactly the size of the underlying block length n. And in fact, we would get back to a place where we can use indifferentiability. But in the spirit of this standards-driven approach, I mean, that's not what the standard says. The standard says this, and so this is fair game. And in particular, like getting these changes implemented might be problematic, but it's nice to know there's a way out if we can use it. Okay, so so we have these 3 projects all in this theme of what I'm calling practice-driven crypto, TLS 1.2 from Tuesday that the other Tom talked about. Provide some new attacks that actually are considered a vulnerability in that setting. Provide some new definitions. Password-based crypto, the a priori seemingly most boring possible paper to write, ended up with some nice, really interesting definitional issues, and then a proof of what we expect, that you get the type of security amplification targeted by PKCS number 5. And then we got to play around with HMAC and show that there's a little bit of cause for concern, nothing dangerous at all, and in particular just ruled out some approaches to proof security. And I should say I expect that one could provide proofs for many of these applications, if not all of them, but we'll have to do some more work. And just as some closing final thoughts, this is not the standard approach, right, of provable security. I mean, I'm basically advocating that in some cases it makes sense to really turn your viewpoint around. We're going to use provable security now as a post facto tool for analysis of deployed crypto, right? And this gives rise to new challenges, right? We have to stick to what's actually implemented or what's actually in the standards. We may not even have existing theory to do this. And this is interesting because this is actually makes it a source of inspiration for new theory, right? A place that theoreticians can find new problems to work in. And on the plus side, if you're successful, you can give nice rigor to the intuition and informal security goals underlying our very important standards, and provide proofs that give us some increased measure of confidence in the standard. And I already said the last part, so I'll just leave with this final thought. Of course, in the ideal world, we should be sitting down together and working these things out, and we shouldn't be doing this post facto approach necessarily. It should be part of the design process. And leave a little bit of RFC-related humor here at the bottom for those of you who have spent a lot of time reading RFCs. Thank you.
Thanks very much. We have a couple of minutes for questions.
Yeah.
I think one of your examples is a good separation between theory and practice, because Ferguson and Schneier were saying, hey, you shouldn't use any of our current functions h, you should use h squared. And people who followed that advice had no trouble with MD5, the subsequent attacks on MD5, for example, or SHA-1. But you're saying h squared is bad because it rules out this indifferentiability proof. And you in fact describe this as a weakness. It seems that indifferentiability is something which is opposite between theory regarding it as a security piece of evidence of security, and practitioners saying these examples are actually h squared is more secure than h is. Bart yesterday was saying output filters are good. That's something where Stefan Lukes proved that you can't get an indifferentiability proof with an output filter. HMAC, everybody thinks is good. And you're saying, oh, it rules out indifferentiability proofs. So there's clearly something different between the practitioner's viewpoint and the theoretician's viewpoint.
Right, I think the problem with that, so the reason we like indifferentiability is because it gives us a tool for providing more support in a variety of settings, right? So if you can show indifferentiability, then we can give you proofs for a bunch of settings that this works as we expect, right? Like an ideal function. I think every practitioner in the world expects their hash function to behave like a random oracle. Okay, and this provides some formal analysis tool for actually providing confidence that that is the case. Now the problem with this, so yes, it's true, h squared and HMAC are fine for many applications. Of course, when it's message authentication, we already have proofs that's good, and more importantly, it is proved well in practice, right? And h squared is also stops extension attacks, seemingly, but we have no evidence that that's true always. And what this actually highlighted, I think, is that as you do this formal approach, actually we realize that maybe h squared isn't good in a setting where you're doing hash chains, which is something I don't think practitioners realize. Okay? And no, so I'm not trying to suggest that h squared or hmac are bad, but if you're going to use them in new settings, you have to be careful. And the problem is in practice, you get these tools and they get thrown into everything. And practitioners, you know, they have some very good intuition about one setting. It may not apply to the other setting. It's very hard, right, to go back and forth. So we're just trying to provide some tools to help us with this analysis. Yeah.
I think that the same spirit, what your result shows is that, for example, it is better to use shorter passwords, you know, at least less than 64 characters, because that's the only case in which your proof works, right?
Right, right.
Or never use 64 characters of password, use
That's
at
right.
most 63.
That's right.
Or
1, 2,
more
3,
than
4, 5 is better.
65 or 63, not 64.
Right, right.
So, so I understand the technical difficulties in proving this, but there is something, you know, not very uncomfortable to have a claim that only works in that particular case. So
I don't
know where the problem is. I mean, is it that that's not the right question to ask or not the right modeling? I don't know, you know.
I don't know.
It's something that you know, doesn't sound that is pointing to something more fundamental or see.
I mean, I think the fundamental thing here is that these hash of hash constructions have this structural property that you can shift things around. And what this work does is it highlights this fact. It was not known before, I think. I don't know of anyone who's observed this. And it's something to be aware of. Now, whether this actually impacts password-based key derivation is not something that our work answered. All we did is rule out a particular way to formally think about this structure's issues in this setting. So I agree, it's not satisfying, right? And I think the takeaway, you know, provable security is not the final word on security, right? It's just another tool in our toolkit for trying to analyze these things, and it gives some rigor to the type of intuition that we have. But at the end of the day, you know, the final word is attacks on deployed systems, right? That's the final word. I think what this calls for is a bit more analysis of HMAC in these settings where we're using it as a general hash function. And I expect that we'll be able to show things formally that matches our intuition that it, you know, it's fine.
Okay, let's thank Tom again. Thanks.